accepted our invitation to fly all the way from Boston to here and share his knowledge and experience in the area of nanotechnologies. And just to give you a very quick background of Professor Busnaina, is William Layton Smith Chair Professor at Northeastern University. He is the founding director of the National Science Foundation's Center for Nanoscale Science and Engineering, and also the High Rate Nanomanufacturing. Also the NSF Center for Nano and Micro Contamination Control. His research support is something that a lot of scientists dream. He put it mildly, I think it's more than $47 million, but believe me, this is a lot, and it is enough, and you know, it's absolutely amazing the quality of facilities at the university which Professor Busnaina has. He had published 600 papers, probably more than any of us, not probably, I'm pretty certain, and he has 20 patents. Organized and chaired more than 175 conferences, workshop sessions, associate editor of Journal of Nanoparticles, and if you look over here at the last bullet, he is in the advisory board of all these great corporations. Fellow of the American Society of Mechanical Engineers and the Efficient Society, Fulbright Senior Scholar, listed in who is who in the world in America, awarded a number of awards. So, I don't think if I can say anything more. It is a great pleasure and honor for me to invite Professor Busnaina.
Thank you very much, guys, Russia, and I thank Technical University Sofia, and I'd like to thank Lara, I am happy to be part of this occasion, the dedication to the new laboratory, and I hope that this will lead to lots of students that work in this area and start their own business here, not just in robotics, but other areas of technology as well. So, thank you, Cassie, for the very kind presentation. So, I will talk today about a new technology that we think is going to change the way we make things. And this is a breakthrough technology that will print telephones, will print chips, flash drive, will print computers. It's going to change everything. So, but first I will take just a couple of minutes to tell you about the university. Northeastern University is more than 100 years old. It's in Boston. It's downtown Boston, right here. And it has about 24,000 students. 1/3 of the students are graduate students. And it has a lot of entrepreneurial activities. They publications, of course, but we also file a lot of patents, for example, to commercialization. I have a few of my students started companies, for example, biotechnology and nanotechnology. And where the university is going. This is about the university. In terms of the center that we started about 9 years ago, the center is led by Northeastern, and it has the University of Massachusetts and University of New Hampshire as members. And as you see here with this table, we have about 39 professors who are in the center. We have more than 100 students in the center, and 20 postdoctoral researchers for a total of 163 people. So the presentation that I'm talking about now is part of that center. The center does a lot of things, but I'm going to only talk about one part, which is the printing of electronics and other devices. And we work very closely with companies. So for example, on our industrial advisory board, we have all these companies. IBM, Intel, aerospace companies like Raytheon and like Lockheed Martin, for example, equipment companies. We have a lot of companies that are polymers, instrumentation, equipment, general technology companies like GE, for example, General Electric, or Kodak, and Intel, Electronics, IBM, Motorola, and so forth. So we work with all these companies. But, so this is just a very quick overview about our center. So let's start with nanotechnology. I'm not sure, I think that most of you probably know about nanotechnology by now. But nanotechnology started with a lecture by Richard Feynman, the Nobel Prize winner. And that was in 1959. I think I was like 8 years old at the time. And he was talking about nanotechnology. Although at that time, no one looked at this. And so he said that the principles of physics do not speak against the possibilities of maneuvering things atom by atom. At that time, people did not even have technology to see atoms. And his prediction came true in 1989, when IBM invented the scanning atomic microscope, and they spelled the word IBM by atoms, xenon atoms. They moved them and they spelled the logo of the company. And since then, people have been excited about nanotechnology, excited about moving atoms, moving carbon nanotubes, moving quantum dots. This is a scale that shows the different scales of things, for example. It goes from, these are MEMS gears, for example, that are in less than a millimeter in size. And then you have fullerenes that are 1 nanometer, and you have carbon nanotubes that are 1 nanometer in diameter, for example. And you have quantum dots, you have graphene. All these things are new material that has very superior properties. For example, carbon nanotubes are stronger than steel, and they're better conductors than copper. And so there's an advantage. The quantum dots, you can make, they have very unique properties, for example, that are better than you can make electronics using quantum dots that are better than any electronics you have today. So, so it goes through the scale, for example. You know, all these materials are here, and we have them. But the problem is that we do not really know how to use them in manufacturing. So the way that we do manufacturing, if you make something large, you cut material and edit it constantly. And you cut, you weld, you deposit material, then you cut again, for example. So you have you're always adding and cutting material. But that's including the chips that you buy today, for example. But the new nanomaterials in manufacturing has not happened yet. And so after all this investment, for example, for it's billions, tens of billions of dollars, we do not have products that have nanomaterials. And as such, we do not take advantage of the nanomaterials. So the electronics we buy today, it's all silicon-based, it's all top-down, and it's all very expensive because they use a lot of power, they use a lot of water, but also the one factor that costs $10 billion. Just one. So there's only about 4 or 5 companies in the world that can actually build such facilities. And no one's taking care, no one in electronics has basically utilized nanomaterials. So the question is why? Why did that happen? Why don't we have something at the nanoscale right now that uses nanomaterials? Well, the reason is because electronics companies like Samsung, Intel, and many other companies like that do not know how to manufacture devices from nanomaterials. They have no idea how to do that. And so, because they don't know how to do that, they have not tried. But how can we manufacture devices or anything else using nanomaterials? Well, actually, you can. And there are some products now that use nanomaterials. They're not high-end products. They're not the best electronics. But there are low-end electronics, means cheaper electronics. For example, if you have flexible display, there are e-books that you buy today that are printed using nanomaterials. Printed using copper nanoparticles, printed using sensors. Most of the antennas in your phones is printed using inkjet printing, and it's printed using copper nanoparticles, for example. So the printing is actually now is being utilized, but it's limited because it can only do micro size. It can go down to 30 micron, for example. And screen printing can go down to about 70 micron. But even with these limitations in scale, they're still much cheaper. So a printed sensor, for example, is about 1/10 of the price of a silicon-based sensor. And in some cases, if it's a complete system, it's 1% of the cost of silicon-based device. So the saving is huge. But the problem is that the scale is not there. You know, they cannot make things as small as the flash drive or the processor you have in your phone. They can only make the large things. And even with this scale, micro scale, the economy is very, very big. Printed electronics now is about $50 billion market. And it's going to be 200 billion in about 8 years or so, more than 200 billion. So even then, it's still very cheap. And so the question is, how can we make the high-end devices, like the processors in your laptop, your phone, the flash drives, the most advanced electronics, how can we make something to compete with that by printing so that it will be cheaper and will be better? Well, you have to do two things. To print at the Nanoscale, you have to do two things. One is that if you do that, you have to do two things to make sure that it can be commercialized and it can be successful. One, it has to be faster than the current printing. It has to be 100 to 1,000 times faster than current printing. And it has to be very cheap. Okay? So we want to make things very, very small at the nanoscale, but we want to make them cheaper than the printing nowadays at the microscale. And we're going to make it faster. So not only you can make it small, but you have to make it small, you have to make it much faster, and you have to make it much cheaper. So what would that do? Well, that would change everything. Because now, if one of you were to start a company and you want to make a chip with nanoscale features, you have to go to the global companies or TSMC fab, and you have to pay thousands of dollars per chip just to try it. This technique can even make your chip for a few dollars. So this technique would be an equalizer. It would be like democratization of nanomanufacturing. So how can we do this? Do we have a very new technology, or do we actually use an older technology? Well, if you look at it, instead of doing inkjet by having a jet that goes line by line and so forth, well, actually you can look at a very old idea, hundreds of years old, printing. The old printing, Johannes Gutenberg printing, offset printing. You have a plate, you ink it like a stamp, and you print it. And this is the way the newspapers are printed. It's offset printing. So we developed the technology, and I'm going to tell you how we do that. We developed the technology to do this, and we developed special templates that you can print nanoscale structures from conductors, semiconductors, or insulators. And we call it nanoscale offset printing. And you can use nanoparticles, any kind of nanoparticles. You can use nanotubes, you can use polymers, you can use a variety of things. And in this approach, we make the template using conventional semiconductor fabrication. I'm going to show you examples of that. And we use directed assembly to ink or to apply the nanomaterials or the ink to the template, and then we transfer. And so this approach gives us 1,000 times faster printing than current technology, and 1,000 times smaller structures than current printing technology. So how does it work? Well, actually, it's very simple. So this is a template that has a pattern. This pattern could contain your circuit or whatever you want to build. And then these are wires, these type of wires, okay? They could be any conductor. You put them in solution, carbon nanotubes in this case, or nanoparticles, and you apply voltage between the two. And this voltage, about 2 to 3 volts, that's it. And you attract all the nanoparticles, or nanotubes in this case, to the template, and you make the structure. And it takes 1 minute. It doesn't matter if you're using a template this big or a template this big. It takes 1 minute. And then once you finish, you transfer whatever you made into another substrate. And then use the template. It's just like printing. Very similar. And so when you use this process, what does it mean? Well, first it's additive. That means we don't do etching, we don't remove any material, we only add material. So you save about, compared to typical manufacturing, you save about half of the processes. Because usually you add and remove, add and remove. Here you just add. Okay? Also, this is room temperature and room pressure. If you compare that to conventional electronics manufacturing today, they use vacuum and they use very high temperature processes. And you can print down to 20 nanometers. You can print on polymer or silicon or any other substrate. You can do multi-scale, so you can have a template that has nano, micro, and macro on the same template. And we use mostly water, so the ink is really water with nanomaterials. In most cases, with the exception of polymers. Polymers you have to use salt. And it's material independent. We've been able to print semiconductor, conductor, insulator, organic or inorganic. So it's very low energy consumption and it's low capital investment because you don't need the vacuum, you don't need the high temperature, you don't need all of that. And so is this good only for electronics? No, not really. You can do a lot of things with the same technology. You can print antennas like we do now, shielding. You can print many materials. This is special materials that will give you special properties, for example. You can make materials that can make things invisible. You can make things completely zero reflection, for example. You can make composite materials, like some of the new airplanes now, for example. They make composite materials like the 787 Dreamliner, which is all polymers, basically. 90% polymer. Or you can make like the Airbus 350, for example, that's already being made. And those use carbon, fibers, and polymers. That's it. So with this technology, you can make them stronger and lighter, so you can carry more passengers and stronger, so that it will give you much more advantage than current airplanes. You can print batteries. The batteries you print, you will utilize the nanomaterial properties. So with batteries, for example, you buy your phone, and after you buy your phone, it lasts for 10 hours, and after 2 years, your phone will last for only 2 hours, 1 hour. And when you buy a phone, you charge it, it takes an hour to charge. Well, the new batteries, basically, you can charge in 5 minutes, and your battery will last for 5 years, and will still have 80% capacity increase. Yeah, we also do energy harvesting. So I'm going to show you all these examples. So you can do energy applications, you can do electronics applications, you can do biomedical applications, sensors, drugs, delivery, and drugs themselves. You can print those also. So I'm going to give you some examples first. Okay. So these are structures made from nanoparticles, very small nanoparticles, 3 nanometers, 5 nanometers, and you can see that we can make 2D structures, individual particles, particles that are arranged in a second structure, or you can make solid 3-dimensional structures using nanoparticles. These pillars are about 20 nanometers in diameter and about 200 nanometers in height. You can make it from different materials. You can make polymer, gold, you can make tungsten, silicon. You can make all kinds of different structures. You can do the same thing with nanotubes. Nanotubes have very unique properties, and you can make electronics from them, you can make structures, you can print the nanotubes on silicon, you can print them on polymer, you can make them 3-dimensional, you can make them suspended, you can do a variety of things. The printing process is very, very flexible and can be adapted for many applications. You can also print polymers, all kinds of polymers. So, for example, this is polystyrene and polyacrylic acid, and this is PMMA and polystyrene. You can make 2D, you can make 3D, you can make a variety of things. So the question is, what I told you now, it's very simple, right? It's wires, apply a charge, you print. So why no one did it before? You know, we're doing nanotechnology now for the nanotechnology initiative that started in 1999. It's been around for 15 years now. No one has done this, so why is that? Did somebody try it before? Well, actually, yes. We tried it before, a long time ago, like 8 years ago, and it didn't work. So what we did is we had the nanowires, like you see here, on insulator, and we applied voltage, like I told you, 2-3 volts, and it worked for microscale assembly or structure, but it didn't work for small scale. So here, for example, you do the inking and you do the assembly of the particles, for example, on nanotubes. The large structures have the right voltage, but the small structures have such a high resistance that you don't get enough voltage, so you don't attract anything. And you can see here, this wire doesn't have any particles on it. This large structure has lots of wires, lots of particles. So it didn't work. It worked only for a micro, but it didn't work for nano. And also when we do printing, the wires are such fragile, so they can break, or they can, if you apply a higher voltage, they can melt. So it didn't work. So a lot of people have tried that, it didn't work. So we had to come up with a new technique. This technique called Damascene template. And this, what this means is that we have all the wires, the nanoscale wires, the microscale wires, and the macroscale wires, all connected underneath with the film. So you can see here they're all connected with the film underneath, and that will give each wire, whether it's nano, micro, or macro, the same voltage, and that means the same electrostatic force to attract the particles, and it makes it very strong. So you will not damage the wires, and also makes it very flat so that you can print very easily. And so this technology that we use is not new actually. The Nanoscale technology is 1,000 years old. It was used to make swords, and it's called Nanoscale because it was in Damascus in the 3rd century, and it died. It died in the 18th century. Nobody knew how to make it and so forth. But then IBM in the 1990s, they brought it with the copper interconnect with chips. And basically it's very simple because you make vias and you deposit copper and then you polish. And we use the same technique. So that's how we make our template, for example. We have silicon or polymer substrate. You do lithography on it, you etch it, and then you deposit your insulator in the oxide, then you polish it, and then you have your template. The template can have any shape of pattern, that you need. And then once you're done, you can make your conductor could be nickel, could be tungsten, could be a variety of different conductors you can use. And so when you print, it's very easy. You have to make sure that the wires are hydrophilic, and the other surface that's next to the wire, such as the oxide, silicon oxide, for example, has to be hydrophobic because you don't want any other materials to go anywhere else but on the wires. And so that can be done very easily by doing functionalization. So this shows you the contact angle, for example, and it shows the process. So this is the inking process, the printing, and then you use it again and again. And so you can use the template thousands of times. So what does it look like? This is what the template looks like. This is the template on silicon, this is the template on polymer. EN, this is the polymer, and this is a cross section of the template, for example. So you can see the conductor goes all the way, then you have the insulator. So this is where you do the assembly, and this is where you do the printing. So this shows some examples of nanoparticles. These are fluorescent nanoparticles. This shows silicon nanoparticles, green silicon nanoparticles that fluoresce, usually the green. These are nanotubes, for example. And the nanotubes, we have a different advantage with the nanotubes because we can align the nanotubes, for example. Now that's very advantageous because when you align the nanotubes, you get a better semiconducting property of the nanotubes. But also, if you make structures, the nanotubes actually are much stronger because they are attached to each other. And so this technology not only prints, but also aligns. If you have fibers, if you have nanotubes, they align them for you. And so this shows an example of how the electronic property changes, and it becomes more semiconducting because the nanotubes are aligned in this case. So I showed you now a lot of small structures. Most of the structures I've shown you are a micron or in some cases 20 nanometers and so forth. But the technology, we apply the technology for much larger structures. So this structure has millimeter size, for example. And you can use the same technology for larger things. So the question is, what can you make with this? We talked about electronics. Besides electronics, can you make other things? Well, I'm pretty sure that you're smart people. You can, if you use this technology, you can make a lot of different things that we have never thought of. So it's a tool that for anybody to use and innovate and come up with new technology, new devices, new inventions that can be used. I'm going to show you some of the applications that we have made. Okay, but that doesn't mean that these are the only applications you can make. You can make a lot of different applications. So, for example, we made new transistors from a new material called molybdenum disulfide. So you probably heard about graphene that won the Nobel Prize 2005-2006 time frame. And graphene was a new material that everybody was happy with, but actually it didn't work out for electronics because graphene is not a semiconductor. Graphene is a semiconductor. It has zero bandwidth. And so in America, in the Air Force and a lot of the agencies are moving away from graphene and moving to a new material. One of the new materials they're using is molybdenum disulfide and tungsten selenide. So we already used our printing process to make devices. So this is a flexible device with transistors that is made from molybdenum disulfide. And then we printed also another circuit, which is an inverter. And this we printed both molybdenum disulfide and carbon nanotubes to make an inverter. So you can actually use this printing technique to do a variety of things. And then you can also do electronics using carbon nanotubes. And this is this device here. You can also print on very thin polymer. This is parity. So you can see these are transistors, and you can see that this is one of my student's finger. You can see you can have a substrate around your finger. It's very thin. It's 12 micron. It's very soft. So you can actually print on any material. We also did use the same technique to do NEMS switch, nano electromechanical switch. You heard about NEMS, micro electromechanical. This is nano electromechanical, and this is a nanotube switch. It's a mechanical switch. So you can use it for memory, you can use it for logic, you can use it for analog devices, amplifier, you can use it for a variety of things. And it's nice because it's like flash. So it's a non-volatile memory. It means that if you turn off the power, it will retain the information even if it has no power. Okay, so this is for electronics. But one of the biggest applications that almost will be immediate is sensors. There's a tremendous opportunity for using nanomaterials for sensors and printing sensors. So this is one sensor that one of my students made, and they started a company to commercialize it. This is a sensor for cancer and for cardiac heart disease monitor to detect the disease years before it starts in the body. So this uses nanoparticles that are locked into these trenches. These nanoparticles are functionalized with the disease. It could be prostate cancer, it could be breast cancer, it could be colon cancer, it could be any kind of cancer. And this is the sensor, for example. It's 0.1 millimeter by 0.1 millimeter, You put it in a catheter, and this is the sensor on top of the catheter. And this has been tested in animals. And you can put 4 different cancers on the same sensor. And all you have to do is just touch the blood with it, and that's it. And so it's very low cost, very cheap, and it has a detection limit that's 100 times lower than current technology. Which means in some cancers you can detect it years before it starts in the body. Most cancers that are very bad, like liver cancer, for example. If somebody, when they discover it, usually the person dies within 1 year. But if they can discover it earlier, they can treat, and people can be cured from cancer. And so there's a lot of companies that are interested in funding this company. So there are a lot of they're going through venture capital. There is venture capital right now. Another sensor that we made also. This is glucose, urea, and lactate. So you know glucose. If somebody has diabetes, they have to check their blood. They have to prick the finger and take the blood and test it many times a day. And that's you can do that, but a lot of these techniques are not accurate. Hospitals don't use the techniques they buy at pharmacies. So we developed a sensor that's like a Band-Aid. You stick it on the skin, and it measures glucose to the sweat. So you don't need blood, only the sweat. And so from the sweat you get the signal, and you put the Band-Aid, and you don't have to change it for like 2-3 days. It will still work. It will work for a week, for example. Same sensor. So and also you can detect urea and lactate. So lactate, that's how tired the person is. So if you have somebody who's flying, for example, and they have the sensor, you can tell that they're very tired. Even if they don't tell you they're tired, you can tell by looking at the concentration of the glucose and lactate, for example. Excuse me. For example. So you can see the signal, for example, every time there's a boost in the glucose and lactate, you get a measured signal, and the signal takes 1 second to get generated. Okay, so this also, the same sensor was used to detect pharmaceuticals in the water system, for example, or bacteria in the water system, or viruses in the water system. Same thing. We also use the same platform to make sensors for the oil industry. So these are people who drill for oil, and they want to find out when they drill, there's a reservoir, and they drill many holes, and they want to find out where the oil is. And so they asked us to make sensors for them. These sensors are very small. They're about less than 1 millimeter. And so these sensors, you can see the sensor here inside, and its functional components will functionalize with whatever you want to detect. For example, the hydrogen sulfide, or thiol, or simple alkanes like methane, for example. And so we developed this sensor, and that sensor has to work at 200 degrees Celsius and up to 10,000 psi. Very high pressure, very high temperature. And we tested it with a company in Boston, and the sensor worked actually at high pressure and high temperature. We also tried something different. We took a chip that somebody made using conventional semiconductor fabrication, CMOS chip, and then we put printed nanotube on top of the chip, and we operated the chip as a sensor. So our technology actually can print on existing chips also. So you can have an existing chip made using silicon, and you can print different layers, sensor or other things on top of it. So it's very compatible with current technology as well. 2 more applications. One is energy storage and harvesting. That's very important. You know, we all use batteries, right? The car has battery, the phone has battery, everything has battery. But the problem with batteries don't really work very well because they don't last very long, and they take a long time to charge. And so we came up with a new technique, which is using carbon nanotubes as scaffolding for batteries. The problem with batteries are being made in the same way batteries were made 40 years ago. They're very, very simple. You have the lithium-based, for example, material, and you put carbon with it, polymer binder, and you have aluminum for the cathode, and then on the other side you just have carbon, lead, and copper, and you have the membrane separates the two. You put electrolyte. That's your battery. It's been made the same way. And your battery, notice that your battery starts very well in the first few months you buy it. It's 100% capacity, so it lasts for 8 hours. After 1 year, it's down to 7 hours. After 2 years, it's down to 2 hours. And then after 3-4 years, it's down to half an hour, right? And then you throw it away. So why is that? Well, because when we store the charge, we store it, we take the cathode to the anode and then take it back and forth. So typically, as the battery heats up and the chemical reaction happens, we lose the lithium, we lose the active material. Because it's basically sitting between particles, so the charge has to go particle to particle to particle until it gets to the lithium manganese oxide, for example, and then goes back. And so when you get space between particles, you can't reach it anymore. So we said, okay, we want to have the battery look like grapes, you know. Each particle is connected to the body. And so we have nanotubes, and the particles are sitting on the nanotubes, and they're connected. They're always connected. So we always have access to it. So we've done, you can see here, we've done, these are the active material, these are the nanotubes, for example. And we get much better, this is charging at 1C, that means fully charged in 1 hour. This is a standard one, 10-hour charge, for example. And you can see the fading is only 5%, this is the fading is 11% at a much lower charge. Most people want batteries that charge very quickly, right? Especially satellites. So batteries on satellites have to be usable for 20 years. And they have to charge half an hour fully. Because when the satellite goes around the Earth, it's facing the sun. Each time it faces the sun, it only faces the sun for half an hour. So you have the solar arrays charging the battery. And so if you can't charge it in half an hour, it's not completely charged. So that's one of the things. We want to have fast charging, and also we want to have less thermal time. And so using this technique, this is a Ragonian plot. So if you're not studying batteries, you wouldn't know what that is. But basically, it plots the power per unit area versus the energy per unit area. So using our technique, we can actually take much more energy. That's very important, because a lot of the high energy material, such as spinel, cannot be used, because even though it's high energy, but you don't have the architecture to get all the energy out of it. In our architecture, we can. And so we've been able to use materials that people have not been able to use successfully in batteries. The other thing is very interesting also. So we always use our laptop, and laptop gets hot. Your phone, when you talk on your phone for an hour, you feel it's hot, right? So you generate heat, okay? And also, you know, when you try to harvest that heat, you can actually get, that's wasted heat. Your engine, wasted heat. So there's a way to actually have that heat and change it into current to charge your battery, for example. So this is, we call it infrared antenna. It's an antenna. So it's an antenna just like antenna in your phone, in your radio. Same. But instead of harvesting the microwave or the radio waves, you harvest thermal waves. And thermal waves are about 1 micron wavelength, for example. And so it's just like anything. You take the waves and you have a NEM diode, and that changes to current. So you have the antenna, you have a very small chip, NEM diode, and then you connect to your battery right away. And so that means that not only you can get waste heat from your laptop or your phone, but also you can have a jacket that has the antenna lining the side, and you can use body heat to charge your phone. So your phone will always be charged. Okay? You can use any heat source from the environment or anywhere. So that means you can use the sun, of course, but you don't have to have the sun. Any heat source can actually give you power. Okay, the last application that we tried is multifunctional structures. So this is a very nice application because it's very straightforward and very simple. So the top structure, this is carbon nanotube. It looks like a grape. It's very similar, but this is shielded. So all the electronics, like your phone, is shielded from other electromagnetic waves, for example, except for the antenna, we never see, because otherwise it interferes with the operation. Airplanes, all the electronics are shielded, for example. But the best shielding is metal. But metal is very heavy, and also it's not very symmetric. And so we designed shielding from it's very conductive. So you can see the resistance here is very conductive. And it's also transparent. The light goes through it. You can see through it. So basically you can make shielding. Also that's smart shielding. For the military, for example, they don't want anyone to intercept their signal. So this shielding basically shields all frequencies except a single frequency that it can be through. So it's like a smart shielding. And so also this could be a conductor, for example, like touch screen. So for example, do you know how this works? Do you know how the iPhone works? For example, when you touch and you have the commands, you know how this works? It's very simple actually. It's a polymer under the glass. It's a polymer, and this polymer has copper wires. These copper wires are 2 micron, and the spacing is about 200 micron. And so as you touch, the capacitive there's a capacitance that goes between your finger and the grid, and then there's pixels underneath it, and these pixels will decide exactly which part of the phone you touch. And so this printed one, we were talking to companies that make the touch screen for Apple, and they said if we use this printing technique, they don't use printing for this. They use positive copper and they etch. So they use printing. They said the cost would be, we can say a factor of 10. The cost of printing this touch screen, for example. So you can do it from the carbon nanotube, or you can do it from copper, you can do it from silver, any other material. So the other thing is that you can actually do what we call metamaterial. So this metamaterial, for example, these very special structures, and when you make them on a surface, you have what we call metasurface. So what does that mean? Well, that means you can manipulate light. So any surface reflects light. That's how we see it, right? But this one, we've been able to reduce reflection to 25%, which means it's almost invisible, invisible light. So it doesn't reflect anything. So that's an advantage because you can do camouflage on airplanes or any other thing. You can, and if you can make things down to 1 nanometer, you can make things very invisible. You saw the movie Harry Potter, right? You know the cloak device, the coat they put on, and they're invisible. Actually, this is possible. This is possible because you design the fiber, or you design the fabric so that the light actually doesn't reflect. It bounces, and then goes around you. So it is possible. But you have to make structures that are 1 nanometer thick to do that. So theoretically it's possible. People have modeled it. But the technology is not there to make things much smaller than we make it today. So now lithography is taking down to 20 nanometer, the structure, the lithography, to make this floating device, the invisible coat, you have to go down lithography to 1 nanometer. But it is possible. The last thing that application is what we call surface enhanced ceramic spectroscopy. This is basically you arrange particles in a certain way so that the spacing is very small, 8 nanometer spacing. And what you do is, and this is used to enhance signal. So you can enhance signal by 10 million or 100 million times enhancement. So for a sensor, for example, you have a weak signal, and you can have this signal by 100 million or a million. So, and we made this very easily. People used to make that before, using silicon and etching and so forth, and it was very expensive. And so here, what enhancement? We got about 100 million enhancement. Okay, so where do we go from here? Well, you can make actually very new, innovative devices and in factories that would cost maybe 50 million or 100 million at the most. And the cost of the printed electronics, for example, would be 1% of the cost that you buy today. Very cheap. And so that means that you can use creativity or innovation to make a lot of new material. But also, we can use nanomaterials now. We can use quantum dots, we can use nanotubes that have much better properties, much more superior properties than silicon that is used today. So we can actually have things that are, chips that are much more capable, have much more capacity, and cheaper. So for example, a transistor, you know a transistor has two values, right? 0 or 1. And to store a word, you need 10 transistors, depending on the word, 10 transistors or up to 20 in some cases. Now they made memristor. And this memristor can store not just 1 or 2, can store 4, 5, 6 values. Okay? So that means you have one switch that can store many information other than the 1, 0, or 1 that we use today. So there's a lot of possibilities. We're working with Urea to make the first offset, nanoscale offset tube in the world. So this is a cluster tool that has the, you've seen the robot upstairs, right? This is the same robot here. Okay? And this tool will print. So you have the AP chamber, you have the transfer chamber, and you have a liner so you can put the layers on top of each other. So this will be ready in May, or April or May. And we will have a big dedication, and we'll invite all the NASA, the Air Force, and Navy, and Intel, and I'm doing this. This has a possibility to bring down 20 nanometers, and this will have a new technology, and we'll demonstrate it using collaboration with